started.
Okay. Okay. Yeah. So in today's lecture, we'll be jumping into a new topic, which is not related to the cache attacks that we have been discussing so far, but it's still related to the security. And at a high level, this topic or this theme can be termed as secure processor or the world of trusted execution environment. So there are a few buzzwords here, trust, environment, execution, and all. So let's start with some definition. So trust is an English word. I don't think I need to define it technically, but here we are talking about trust in the context of you know computing, right? And then the machine that we are using or the entities that we are using. Let's say our operating system, hardware, network interface card, right? Anything that we use to compute in today's world, right? So there is a technical term here, which is trusted computing base, which is nothing but a set of hardware, software, firmware entities that we kind of assume to be secure, right? So if I ask you like what is the TCB for your laptop, you can say that okay, maybe operating system, my processor, okay, and that means you are assuming that these are the entities which are by definition, by design, they are secure, okay. And once we have defined like what exactly is a trusted computing base, then we can come up with an environment where we can run code or we can access data in a secure way. So for example, if I'm doing a bank transaction, right? So let's say it involves pretty secret kind of code segment and then and cryptic kind of code segment and the data access that those bank transactions involved with, I would try to make sure that they are not accessible by anyone else, right? When I am doing the computation on any computing device, it can be a desktop, laptop, server, in a cloud environment, right? So TEE in short, or the trusted execution environment, is actually it's kind of a software environment, right? That provides you a feature for creating, running programs. Basically, you can run your binary, and it involves both code and data, right? And it makes sure that it's secure. When I say secure, if you remember the very first lecture, the confidentiality, integrity properties come into picture, right? And running a secure code or process is actually termed as enclave, as per Intel Trusted Execution Environment, which is Intel SGX. We will go into that in detail in few minutes. But this is another dimension. So we have the notion of process, but now we have a notion of enclave process. So where you are kind of sandboxed into a secure environment where the code, the accesses that you are doing to memory are supposedly to be secure. Okay, so they are by definition they are secure. They should not leak any information. Okay, but if you look at all these definitions, that means there is a boss who is actually providing all these guarantees that yes, there is a secure environment. Your core data will be secure, and whatever you do inside that trusted execution environment, it's kind of 100% secure, right? So who can be responsible for providing such an environment, right? So the obvious answer that you can think of is an OS, right? Because the OS actually makes sure of many system level activities, starting from booting up the system and allocating resources and blah blah blah. But what if the OS itself is malicious? What if the OS is compromised? So think about a server or a cloud provider where let's say the OS is kind of compromised by various reasons. Okay, that there are various possible ways through which, let's say, someone has actually got control of an OS, right? Then if you provide the root of trust to the OS, then the entire system will be collapsing, right? Entire system will be compromised. So instead of that, what modern systems do is that they use another entity which is known as trusted platform module. It can be a software, it can be hardware, it can be firmware. There's a different name for it depending on which commercial company is providing you the trusted execution environment. It's also known as secure monitor management or just security monitor kind of, right? And the job of this guy is to boot the system to start with and verify each and every process that is part of our program execution, before program execution and during program execution, and even after the program is executed, right? So you can start with the BIOS, right? So the security monitor should verify that the BIOS is trustworthy. So how it ensures that? Okay, so there is a significant amount of crypto used in trusted execution environment. I won't go into the crypto part, but that's not the focus of this course. But you can assume that for each entity in the trusted or TCB, the computing base, there is a notion of hash. There is a notion of signature. Okay, and the security monitor actually verifies those hashes or the signature to make sure that okay, this particular entity is actually secured, and then I should include this particular entity in TCP. Okay, if any entity fails to provide that signature or hash, then that particular entity won't be part of the TCP. Okay, so in fact, if you look at the sequence of events that happen, starting from booting your system, making sure that you're loading your OS pages, pages for your binary and blah, 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 you'll find that there are a series of events that are happening. And for each event, there is an entity. So it's kind of a chain of trust. And for each entity, the security monitor will actually make sure that the entities actually prove themselves, saying that, OK, they are the best guys to do this job. OK. So if you look at from end-to-end picture, initially you start with a hash while checking with the BIOS. Then finally, once you are done with checking with all the entities, you'll get a final hash, which is a hash for the entire TCB. If your TCB includes OS, CPU, cache, DRAM, then every entity will actually provide you a hash. And finally, it will be a multi-level hash. Hash one, then hash two, then hash three, and like that, right? So with that definition, let's look into a 10,000 feet view on Intel SGX, like what exactly it provides. So all of you must be familiar with the notion of OS process, right? You have the data portion of a process, a code portion of a process. Now, if you want to do something which is supposed to be secure, right? Like you want the code and the data should be secure and it should not be compromised. It should not affect the confidentiality and integrity. You can actually use SGX, which stands for Software Guard Extension. So these are a series of instructions that are provided by Intel that ensures that okay, you create a memory area or uh, a space inside your DRAM where that particular space is actually devoted to a particular enclave or the secure process, right? So now each enclave will have its own code and data, and then there will be checks every time you want to access this code and data, similar to your page table walker, right? So whenever you do a virtual to physical address translation, there are various checks that happens. Here there will be some additional checks that will happen that we will see. Okay. So this is the entire picture of Intel SGX. So if you assume that SGX provides some runtime through which the end user can actually write a function or write a entire code that should be inside an enclave. So these are the various instructions. No need to remember it. If you want to play with it, assuming if you have a recent enough laptop, I assume Intel SGX will be there. You can just start using it. Intel provides I think it provides a framework also to start with some demos and then some toy examples. But nevertheless, so the key thing from the architecture point of view is we used to have our basic translation, virtual to physical translation through page tables. And now what happened is because we said that, okay, enclave has its own restricted memory space. So we have these additional structures or data structures. Basically, it's called enclave page cache. And there is a manager which manages all these pages. So these are the pages that are allocated to enclave. Okay. So you can assume, or you can think about a program where there are few functions which should be secure. Let's say there are other functions which are kind of pretty ordinary functions. You don't need any security guarantee. You can run them in a normal mode. But if there is something which is pretty crucial for your organization or for your own data confidentiality integrity, you can actually use the SGX runtime environment, and they will be using those pages. Like they will be uh, using pages from the EPC, and the EPC manager will actually track of, okay, how many pages have been allocated to a particular enclave or whatever. Okay. So again, so there are various instructions here. You can correlate based on the names, but that's not the goal, at least for this lecture, because otherwise it will be a tutorial on the programming environment, which I don't want to provide at this moment. Okay. So at a high level, I about the crypto part, but the way Intel SGX at least provides or guarantees security is, it assumes that the CPU is secure, but the off-chip memory is not secure. So you can think about servers or data centers, right, where memory chips can be coming from various third-party vendors, and that's why what it does is it makes sure the data that is stored in DRAM is actually encrypted. Okay. And so again, I'm actually showing all these things in terms of definitions. So whenever you want to store the data in your DRAM for enclave, you have to store it in an encrypted form. Okay. And let's say you want to get the data from DRAM, you have to decrypt it. Right. So there will be additional latency now because you need to perform some additional checks along with the normal load request that you use to check at the cache and DRAM. Right. Um, there is another policy which is actually known as the MR enclave policy and MR signer policy. So these policies are actually used for something called attestation or data sealing. So for example, let's say there is one enclave or the secure process or part of the code, and that guy wants to communicate to someone else, which is also secure, which is also enclave, right? So how can that particular communication can happen? What is the protocol? So these are the various policies through which.
Sure. I
Yeah,
have
is there a
one
question?
question.
Yeah, sure.
Yeah, question. So why they have focused only on encrypting data in DRAM? Why not in LLC also?
Yeah, so that's the problem. I will jump into it at the end. So their definition was, if you look at the very first paper that came from SGX, they assume that the CPU is secure.
Okay.
So anything that is part of CPU, like caches, all the microarchitecture units that we have discussed, SGX assumes it's secure.
Okay.
Okay.
So only security they provided is by encrypting data in DRAM.
Yes. So anything that is not part of CPU is actually untrusted, as per the trusted computing base.
Okay.
Okay. So similarly, it doesn't trust the OS. So that's why the notion of security monitor. It's a one level higher, software or firmware entity that makes sure that your system boots up, and then all the typical OS activities are actually now done by a security monitor instead of an OS. Okay.
Yes. Okay.
Okay. Yeah. So as I was saying, if there are two enclaves, they want to communicate, or let's say that there is some data that is generated by one enclave and another one want to process it, consume it, then there are different policies through which these enclaves have to operate. So these are like MR enclave and MR signer are the policies where again it's full cryptography where you need to create a signature, you need to verify that signature. Both the parties will finally actually agree that yeah, whatever signature was generated by the another enclave is actually expected. I was expecting the same enclave. So finally they say that yeah, there's a green signal from both the side and now we can start communicating. Okay. This is for enclaves trying to access something from the another enclave. But what if there is a normal access, right, which is not inside an enclave, and that tries to access something which is inside the enclave, right? So let's say you are doing a simple quick sort function, and that quick sort function was trying to access an address which is part of an enclave. then this will generate a new technical term called page abort. You must have heard about page fault, right? In the normal, but basics of OS course. But page abort is a new term which is used when a non-enclave access or a non-enclave code or data is actually trying to access something within the enclave. Okay. So this is the entire process of attestation and sealing. So there is a notion of remote attestation where enclave can verify itself by sending a hash signature or report to a remote Intel server. Okay, and the Intel server finally will say that this is actually a valid signature, and for the machine that you are using, uh, like now you are the boss, you can actually do all the security critical operations. Okay. So again, I don't want to go into the crypto part. If you have done any course on crypto, then you will be able to get a feel about, there will be exchange of keys. Then finally there will be some verification, and then they will start ensuring that yes, these are the right step to do, right? So this is one example that I was showing. So if you have started with, let's say, EAD is an instruction which is adding an enclave. And if you look at the various instructions as in when you use, let's say you want to extend the memory space that you have allocated for your enclave, and every time you extend it, so you generate a hash, right? So finally, let's say that this is the entire sequence of events that you have done while creating and using an enclave. So this is the final hash for your enclave. Okay, so if you want to access anything which is which is supposed to be accessed by this particular enclave, then this particular hash or key is actually the the key to the lock or the data or the code that is stored in the different parts of memory, cache, or whatever, right? So this is the access control mechanism to put it at a high level, like 10,000 feet view level. Okay. And this is what I just discussed few slides before. So this is from Intel. So if you know the notion of linear address, which is nothing but the virtual address, uh, the basic page table checks will happen. It will generate a physical address, but now there will be additional checks. The first thing is it will check whether it's an enclave access, right? And then if it is, then it will check whether the address is actually present in the enclave page cache, and it will check the enclave page cache manager. If all the checks are passed, then it will allow memory access, otherwise it will generate a fault. Okay. And if the request is actually not an enclave access, but the address is actually within the EPC, that means a non-enclave request is trying to access something which is present in the enclave region. So it will generate a page abort. Okay. And if this condition is false, that means the address is not inside the enclave page cache. That means it's a normal request to the normal page, normal OS page. So it will allow the memory access. So from the architecture point of view, this is actually key because some of the recent attacks that appeared in Intel SGX or some of the pretty early attacks on Intel SGX, they exploited this part. Okay, we'll see that in few minutes. So this is the entire summary of Intel SGX. It tries to isolate a secure code or data, creating an enclave, which is at the application level. So if you understand the notion of OS rings, it's actually at the ring 3 level. Sorry. And you can actually perform attestation, verification, and everything, even locally, or you can do it through a remote platform. You can actually send it to an Intel server, which will verify and send you a green signal. As I have already mentioned, the DRAM is actually considered to be untrusted. That's why the data is stored in the encrypted format. Okay, so every time you try to access DRAM, you have to decrypt it before you get the actual data. Okay, so this is the high level summary of Intel SGX. Any doubts so far? I'll take another 5 to 10 minutes, then we can start presentations.
Biswa,
Yeah.
uh, if I presumably assume that this enclave is implemented at LLC, so we can
No. Enclave is not LLC, right? Enclave is the memory space. So let's say my DRAM is 4 GB, right?
Okay. Yeah.
You say that, okay, out of 4 GB, you provide 100 MB for enclave.
Okay.
So let's say from address number 0 to address number 128 MB is the enclave address. So the enclave page cache will actually now start mapping any virtual address which is part of enclave into 128 MB region in the DRAM.
Okay. Then in the previous slide, then why are we accessing the memory on a page about?
No, we are not accessing memory in the page about.
There is an arrow showing allow a memory access on a replace address with about page. I was not clear.
So that's a replace, right? It's a page replacement.
Okay, page replacement inside the enclave.
Yes, inside the EPC.
Okay.
Yeah, because the address is actually inside the EPC, right? So.
And this enclave is actually helping us save ourselves from the speculative kind of attacks, right? Because
No,
of this.
no, it doesn't. It doesn't. I will come to that. So let's not get into the attacks at this moment. Let's understand what it provides at a high level.
Okay.
Okay. Any other queries? Okay, so let me jump into it. So there are other companies like AMD. So they have their own trusted execution environment. Okay, you have a question now.
Yeah, I have I was having network issues. Sorry.
Okay.
So can you go in the previous slide? Yeah. So this attestation process, this can happen over the network, right?
Yes.
So it's also vulnerable to like network attacks also. Is it?
No. It's like before accessing anything, you are verifying yourself. And let's say the verification entity is somewhere sitting in California, right? So you are actually generating a request saying that, okay, could you please verify? So attestation is nothing but, proving yourself that you are worth of accessing this particular machine or the TCP.
Yes. So that can also be like vulnerable, right?
It's all, the data that you will send is completely cryptographically.
Okay.
You will actually generate a 256-bit signature, right? And then depending on the cipher that you use, let's say SA or AES or whatever. I don't think anyone will be able to get anything. Only the Intel server will be able to decipher what exactly it means.
Okay.
Right? Yeah. And then initially the key is generated by the CPU itself, because Intel SGX assumes CPU is secure. It's sacrosanct. Okay. It doesn't trust the memory. It doesn't just trust the OS, but it trusts the processor, saying that, okay, this processor is actually secure.
So this attestation process is just for verification, right?
Exactly.
Okay.
Yeah.
So this attestation will happen, at the very start of the system also?
Exactly. The moment you create an enclave, not very start of the system, but you create an enclave. When you create an enclave, that time you need an attestation. If you are running a simple C program, why you need attestation? There is no need of security, right?
Okay, so whenever an enclave access is there, but
when you create an enclave, it will generate instructions the way you have add, load, store instruction, right? Similarly, it has various kinds of microarchitectural instructions which will actually send this particular key that we have been talking about to the attestation entity or the unit, right? And that guy will send you saying that, yeah, everything is okay, you can move ahead.
But the BIOS imprint, which were discussed in the earlier section, that has to be done at the start of system only, right? I mean,
yes.
Afterwards,
so that will be done by the security monitor. That's what I'm saying. But here, given an application, let's say you are building a web server, right? And you want some part of your web server to be secure.
Okay.
Right. Then only when you start executing or you start including some SGX related code, which will be part of some enclave, then only you need to verify that, yeah, everything is correct, right? Otherwise you don't care, right? Finally, whatever happens, it doesn't matter, right?
Okay,
because
so
from at the user level, you are not concerned about security, right? So for example, if you are submitting your course project or course assignment, it's not a big deal, right? If someone steals it, what's the big deal?
Yeah. So the initial check will happen, but it will store. It will not send that anywhere till you have an enclave access.
No, so think this way. So initially, the security monitor will do everything that we have been discussing.
Okay.
Allocating pages, blah blah blah. Some fixed limit on how many pages I can allocate, depending on whether it's Intel, AMD, ARM, or whatever, right? But the moment you say, okay, can I access this particular address? Let's say the way we have process ID, right? Similarly, you will be getting enclave IDs now, because within each application you can have multiple enclaves. They are like tiny subpart within a big program. Okay.
Okay.
So your program, let's say if your program has 100 functions, and out of 100 functions you say, okay, I need the 6 functions to be inside enclave. Right? So then you use Intel SGX, the runtime environment, and then put those code inside the SGX environment, right? So then it will initialize an enclave. It will verify that, yeah, these are the address space that you are supposed to access. No one else should be able to access it. So these are the sequence of events that will happen.
Got it. Thank you.
Yeah. Okay, so let me jump into it before taking further questions. So AMD has a similar, trusted execution environment, but this is more scalable compared to Intel SGX. So Intel SGX, when it came to market, it had a limit of 128 MB of enclave space, or the EPC. Okay. Later it jumps to 256 MB, but AMD doesn't put any limit. So this AMD SEV stands for Secure Encrypted Virtualization. Similar concept. The goal is the same. The Intel counterpart actually does a attestation through, the remote attestation by generating a key and all. So AMD instead, what it has done is it has put a secure processor inside your chip. Okay. So anytime you want to verify yourself that, okay, whether you are supposed to access a particular address or not, you can actually send your key to the secure processor or co-processor, which is sitting along with the processor. And that guy will actually give you a red signal or green signal, then only you will be able to access a particular memory address. Okay. So based on the page size limit, you can easily conclude that, Intel SGX was actually designed for small and secure code, which is like pretty tiny. You want to run highly security critical code, but this AMD SEV technique is actually not limited by your DRAM. Oh, sorry, not limited by few KBs or MBs. In fact, you can run, large servers, big enterprise applications inside enclave. So imagine running your entire database server inside enclave, right? So that's possible with AMD SCP, right? But with Intel SGX, it will start giving you faults, page faults, because only 128 MB is allocated for enclave. Your database will demand 4 GB. So every time you send a request for enclave, by the time you do a load and store, there will be a page fault. Okay. So in terms of performance, AMD SCP is better compared to Intel SGX overall in general. Then for your mobile phones and all the handheld device where ARM processors are there, similar concept, trusted execution environment, but here there is no notion of this data storing in encrypted format and blah blah blah. Although you have a notion of security monitor, which switch between two different modes. One is the normal world where you have a user process, kernel process. Maybe if you have a hypervisor that manages multiple virtual machines, and the moment you need, let's say, the security critical code, you want to execute security critical code, then you can jump into the secure mode of the CPU. Okay. This is if you compare this idea or this technique compared to Intel SGX, this technique is actually designed in a more disciplined or principled way. So if you look at everywhere, starting from registers, DRAM, cache, SRAM is actually your cache, right? Any other interface, it is actually partitioned properly or they are duplicated. That means there is no possibility of all these side channels that we have been talking about. Okay. So compared to Intel SGX, ARM Trust Zone is if you have to quantify the kind of attacks that are coming up, ARM Trust Zone will be hard to attack compared to Intel SGX. Okay. There is open source version of trusted execution environment, which is RISC-V based, But the RISC-V is the open source ISA, which is available, publicly available. So you can actually go to this website and you will be able to download a trusted execution environment, which is designed only for RISC-V. Okay. Similar concept, I think it borrows the best part of Intel SGX and ARM Trust Zone. It partitions cache, it makes sure that other kinds of side channels doesn't happen. And at the same time, it provides all other things like the data is actually in the encrypted format. Okay. So go and have a look at it if you are interested for open source trusted execution environment. And finally, as I was talking about accessing DRAM, as it is untrusted, every time you write something into it, meaning the last level cache will actually send a write back request on a replacement from the LLC, it will actually go through an encryption engine. Okay. And similarly, if you are sending a load request that is missing in your cache hierarchy, and finally it's coming from DRAM, then you have to decrypt it. So this encryption and decryption will add extra latency on top of your existing memory hierarchy latencies. So obviously the performance will go down for all these regions. Now the question is, how secure is SGX? When it came to the market, it promises that, okay, it takes care of confidentiality, integrity, and blah, blah, blah. But these are some of the titles of attacks on SGX. So you can see, SGX is actually changed to something called software grant exposure. And everywhere you will find cache attacks, as I think someone has rightly mentioned, right? Whether it takes care of cache, no, it doesn't. But there is a subtle point here that the first attack that came through SGX is actually through page faults, and it's not through the caches, it's through the page faults. And I'll provide those papers as the reading assignments or review assignment. But at a high level, what happens with page table based side channel, especially with enclave, is, so let's look at the simple function, right? And the star A and star B are two different memory addresses, right? These are pointers, so memory addresses meaning different OS pages, the memory pages, right? So if you look at, depending on, again, there is a data flow, control flow dependency here. Depending on the outcome of particular value secret, you access a particular page, right? So let's say if this condition is true, you access memory page, let's say A, otherwise you access memory page B, right? So at a high level, whatever we have discussed so far in terms of cache, you can correlate that, oh, okay, so something similar can be created here. But I will leave it to you that why this can be possible with Intel SGX. And can someone guess at this moment why the space table side channel is a big deal with Intel SGX? Just think for a few seconds, maybe maximum for a minute.
Out of order execution?
No, out of order is the CPU part, right? That will come. That's there. There are attacks which actually exploit. Remember, I talked about a page abort. If someone who is not inside an enclave and is trying to access something which is inside the enclave, remember that, right? The page access flow. So even if it actually generates a page abort, it actually goes ahead and then try to get the page table entry, and it caches the page table entry. So that's what it's showing here. So depending on the control flow and then the conditions, right? Irrespective of whether you are inside enclave or not, the cache hierarchy will have the page table entries. Okay, even if you abort it. So that means as an attacker, I can actually try to send request to enclave addresses, which will eventually be aborted. But the page table walker will actually go and then get the page table entry into the cache hierarchy if it is not there in the page table. Okay. Anyway, this is at the high level. We'll provide that as a review assignment, which will be much more clearer. And then, as Sasank was suggesting, the notion of out of order and speculative execution. So there's an attack which.
Okay.
Is
the
there a
previous
question?
slide, you can explain, yeah.
Yeah.
How page table attack is possible, like bringing it to cache and then you were suggesting something. I could not understand that.
No, the basic idea here is, even if you get a page abort as an outsider which tries to access the enclave address, right?
Yes.
the corresponding page table entry, right? If it is let's say you are getting an abort, but you want to access some address which is actually part of some enclave, and let's say that is not part of your actual page table for obvious reasons. Now the page table walker will go and get the page table entry, assuming it's a fault. Are you getting me?
So you are trying to access you are saying so. So I'm trying to access an enclave, let's say page portion.
Exactly. I'm trying to access an enclave page now. Yes.
I'm not like eligible to access because I am from
exactly. Yes. That's
So
why, as per the access flow, it doesn't allow, right?
Yes,
It throws you an abort.
a page.
Yes.
So are you saying that Intel SGX will abort my request but still bring the page from the I don't know, maybe from so where it will bring the page table entry to the
page table entries are there in the DRAM, right? So you have to bring those things from DRAM into the memory hierarchy, into the cache hierarchy.
even after giving me abort.
Yes.
Okay,
So that's the attack. If you look at the bottom of this slide, telling your secrets without page faults, because even the page aborts will give you information. So that's the paper, but I don't think I'll be explaining the attack now line by line. I'll provide that as a review. Okay.
Yeah, okay, Vijay.
Okay. Yeah, so this is just the extension of what we have already discussed, the notion of Spectre attack, right? You can do the similar thing even inside Enclave, even with Intel SGX. And this attack is known as foreshadow attack. Okay, you do the Spectre Live attack, but inside an Enclave now. Okay, so all these attacks I will provide as reading or review assignments, maybe a few weeks down the line. I'm not explaining each and everything because at a high level, the basics are similar or the same. You're trying to create a timing channel because of some hiccup here and there, and then you're kind of exploiting it, right? So yeah, with that I will stop. Devasis, you can stop the recording and we can start the presentations.